Okay. So last time I talked about a model which is the one of biased random walks on Galton-Watson trees with leaves, which was essentially just that you took a Galton-Watson tree with leaves that's supercritical, and you condition it to have an infinite line of offspring, so you get some kind of drawing like this, with parts going to infinity, and certain leaves like this one. And then on it, you did a biased random walk, meaning that you had a chance beta times higher to take an edge going down than an edge going up. And the point that I wanted to make is that this model, although it's a tree, actually, if you want to look at long-time behavior, behaves as a very simple one-dimensional model known as the Bouchot trap model, the directed Bouchot trap model, which is just imagine a line, and on each site you put a waiting time, which is exponential with mean tau I, and the tau i's are IID. And so basically, in this model, what we get in the long-term limit is something called a stable subordinator, which means that essentially it's some sort of jump process, which looks a bit like this. An alpha, so long-term limit, and you get an alpha stable subordinator in the case where the tau i's are heavy tails. And also from this model, you can deduce properties like aging, which explain that the system gets stuck at very long time in the same state with positive probability. And so basically, the idea is that if you understand this model, I want to justify why you actually can retrieve information on the biased random walk on the Galton-Watson tree. So when you take this picture and you want to say, okay, how is this similar to a Bouchot trap model? There are several questions coming up. So a first question is, well, this is a tree, and well, we're supposed to be one-dimensional. So one natural question is, where's the one-dimensional thing in this picture when we have an entire tree? Another question which comes up is that in the Bouchot trap model, the waiting times which are supposed to represent traps are independent. And when you look here, for example, here we have a leaf which acts as a trap. Here we have a leaf that acts as a trap. But the time that's spent in them is not completely independent, because let's assume that you have like 1 billion visits to this point. This is going to influence the time spent in both this trap and this trap, because if you spend 1 million units of times here, it means you're very likely to enter a lot this trap, spend a lot of time in it, and you're very likely to spend a lot of time in this one because you enter it a lot. So there's this issue of independence. I never know in English it's with E or A. It's E. So why is there independence? And another key question is to understand the tail of the time spent in traps. In particular, show that it's heavy-tailed. And also one other kind of minor aspect is to show that, well, in this case, the traps are not points, so they're actually like subtrees. So why can you say that traps are points? This is really a minor issue, but I'll still go over it. Traps are, in some sense, points. So those are essentially the hypotheses we would need to justify in order to say that this model behaves like a directed one-dimensional Bouchot trap model. So I'll try to explain all this, which will lead you to believe that actually the long-term behavior of this model should be like the Bouchot trap model. And actually it turns out that in this specific model, there's a slight tweak due to some lattice effect that makes some strange result appear. And I'll try to elaborate on that later in the talk. So the first key part to understanding this model is really to understand this dichotomy between traps and like the main part of the tree. So what you see in this picture is that, well, basically what are traps? It's all those points which have a line of descent which is finite, which means that if you keep going with the drift, so keep going towards further away from the root, you'll eventually hit a dead end. And so we need some way of decomposing this tree into a part which is nice, where you have ways to go to infinities which are direct, and like those big leaves. So there's a really nice way of making the decomposition, which is called the Harris decomposition, which actually tells you that if you start with a Galton-Watson tree with leaves, that you condition to be infinite, which is exactly our setting here. So what you can actually do is you can decompose it into a Galton-Watson tree without leaves.
Not the best choice of color.
Okay. I have green and yellow, that's better. I have red also, so let's see. Not good either. Not good either, for different reasons. So a Galton-Watson tree without leaves. And we'll call this part the backbone. And another type of Galton-Watson trees, so which are subcritical, which we'll call leaves or traps. And so the way you can actually construct this white Galton-Watson tree is by starting to construct this yellow Galton-Watson tree without leaves. So it's a nice tree where like you don't have any traps anymore. All of those things go to infinity, which means that the bias should not be able to trap you anymore. And basically what you do is that this tree is going to be decorated by those finite Galton-Watson trees or those traps. Poof. Which for our purposes is really perfect, because this backbone is like a highway to infinity, and what's the annoying part for us are all those traps. This is what creates the trapping. The trapping is really completely encoded into this red stuff. And so not only do we have a decomposition in like backbone and trapping parts, but the law of this is actually explicit. And I really enjoy this Harris decomposition because there's a really nice drawing which makes you understand how everything works. So if you look at the generating function of this Galton-Watson tree, so meaning this series, pk zk, k from 0 to infinity, then what you know is that f of, let's say, t, I used z. Well, you know that at 1 it's 1. You know that at 0 it is p0, which is positive, and you know the tree is supercritical, so the how is it called? The slope at 1 is bigger than 1. Also, it's a concave function, so it looks something like this. Convex, yeah. And we know that this is the probability of extinction, q f of q, which is a fixed point. And so the very funny thing is that you see that in this picture you have two squares, one here, one here. And what happens is actually if you take this square over here, magnify it up to have size 1, you actually get the generating function of the yellow tree. and if you take this red square here and put it up to size 1, you would get the generating function of the red tree. So this is actually, as you see, the generating function of a subcritical tree, because here the mean is lower than 1. And in this yellow square, you see that at 0, you're at 0, which means you don't have any leaves. So this is the Harris decomposition. So this is useful to us for only one thing, and the key information here, I don't know why I write in red. The key info is that the Galton-Watson tree that forms the traps, so they're subcritical, and the mean of that tree is actually known to us, and it's the derivative at this point, f prime of q. It's lower than 1 because it's subcritical. So now we're in a real nice setting. We have a part of the tree where we go fast. We have those traps, and we actually know the structure of these traps. And now, if you recall, I had told you a theorem of Lyons, Pimentel, and Perez. Which was from 96, which told you that the long-term behavior of the walk was that it had a limiting speed, and there was a dichotomy between the speed being positive for small biases, and actually for small biases, lower than a beta critical, and actually this beta critical is this 1 over f prime of q. So last time I just told you that there was a critical bias. Now I give you the value. And so this is for the kind of general pictures. So now I'll go back to what my initial point was, which is, okay, let's explain those 3 points. Let's explain why it's one-dimensional, now that we know exactly what the traps are. Let's explain the independence between traps. Let's explain the time spent in traps, and why traps can be considered as points. So what we want to look at, the quantity we're looking at for now, let's look at the following quantity, delta n, which is the first time you'll reach a point which is at distance n from the origin. So this is the same as saying distance from the root to x and xi equals n. So basically, you have your tree, ding, 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 with small parts hanging off it. And you look at distance n, and you wonder, how much time is it going to take for me to reach down to this point? And so the first thing that we can very easily explain is, is going to be this one-dimensional thing. So what's the one-dimensionality here? So, okay, we have a lot of ways to go to this level here, but actually, if you think about it, what we have is actually a biased random walk, which is going to discover this tree. So to simplify the picture, let's imagine that beta is bigger than 1 for now. So the reason why I make this assumption is that actually, if you look at this theorem, the zero speed regime is for beta bigger than a beta c, which is this number here, and this number happens to be bigger than 1. So this beta critical is actually bigger than 1. So if we want to see the trapping anyway, we have to look at this regime. So we have this picture, and what happens if you have a biased random walk on, so let's put the traps in red. What happens for the biased random walk on this backbone part it actually goes very fast. It actually goes faster than a biased random walk on Z. So it actually goes forward very quickly. It might backtrack a little bit along the backbone. Ding. But essentially, it looks one-dimensional. Sometimes it will spend some time in a trap, and then go back on the backbone, and essentially go in a pretty straight manner up to this point. So what happens is the following thing. The biased random walk on the backbone. So what I called the backbone was this part with no leaves, Galton-Watson bar, is very, goes very straight forward. It actually explores a very small subpart of the whole tree. The whole tree has an exponential number of ways to go to infinity, and what I'm going to explore is essentially a one-dimensional thing. So in a tree which is big, I only see a one-dimensional subpart. So this explains why actually the model in some sense is one-dimensional. You have a lot of different opportunities, but when you actually run your experiment, you just see a very little subpart of it. So this explains why the walk is one-dimensional. Also, because of this, you can explain why the traps can be viewed as points. So the reason for this is, so let's say this is the trajectory of my walk along the tree. It looks something like this, very one-dimensional. And I want to go at distance n. And what I'm going to see is I'm going to see traps on my way. And there would be an issue if those traps were of the size of the system. If those traps were of size n, this would actually be slightly annoying to me. But actually, it turns out that you can prove that those traps are very small. And the reason for that is that the probability, let's do it like this. Okay. So those trap parts are subcritical Galton-Watson trees. And if you look at their size, so I'll just measure that by their height, we can actually see that the probability that the height is bigger than n has an exponential decay with a known parameter. So actually it means that along our trajectory, we have of a linear number of trials to get traps, which all have exponential tails. So actually all the traps have size which is at most logarithmic. So actually in the limit, when n goes to infinity, those traps just looks like they were points. So this here, the 1D part, the 1D part, this comes from the walk. From walk seeing a subspace. And this traps or points essentially comes from the same parts. So one-dimensionality plus tail on size of traps. So what might be a bit more tricky to understand is why traps are independent. So as I was saying on this picture, if you take any two traps, they might have a correlation because the number of entries to them are similar. But what actually does happen is that if you remember the picture that we got from the Bouchot trap model, it's that if you want to understand the long-term behavior, there are small traps, deep traps, essentially. There's these two parts. Small traps don't contribute to the limiting behavior, but very big traps account for all the time that you need to go to infinity. You can actually see that on this picture of the stable subordinator. For a while, nothing happens, and then you meet a big trap and spend a big chunk of your time in it. Then only small traps doesn't really matter, and a big chunk of time in one big trap. So what happens is, so Y independence. What happens is that our intuition from the Bouchot trap model tells us the following thing. Only big traps, only the biggest traps matter. And more precisely, when I say biggest, it's essentially a finite number of them. And why is this good for us? If we look at this picture, we have from 0 to level n, our whole behavior is actually explained what happens in a finite number of traps. So in this picture, for example, I have, let's say, it's representative, and we have 4 traps that account for the whole behavior of the walk. 5? Yeah, I can count to 5. Interesting. So we have 5 traps that account for the whole behavior of the walk, and they're distributed along a length of n. So what happens is that the distance between 2 important traps is huge, which means that actually all this phenomenon that maybe, it's very unlikely in this case that the time spent in this trap would have anything to do with this, because for the walk would have to kind of go in between the two to transmit information. So the traps are very far away, so they have completely independent behavior. That's kind of the idea. So finite number of traps, so big traps are far away. And somehow the fact that you get far away means that you lose any information. And explains the independence. So this is very similar to what Gérard was explaining in the spin glasses also, that you see a big trap, then you start walking around, and in a certain amount of time, you actually lose all information about your past. Here, the exact same thing happens. You have very few traps. They're far enough away so that you don't have to take into account independence if you want to look at long-term behavior. So this comes from basically few traps governing the walk. Few traps governing long-term behavior. So the only thing I still need to verify to say that everything behaves like in a Bouchot trap model is to look at the tail of the time spent in traps. So I'll go over here. So our trap is this Galton-Watson tree. Looks something like this. It's subcritical, so it's not very hairy. And it has a certain height. And what you should imagine is that over here, somehow there's the backbone going. So if you want to look at the time spent in the trap, I'll just give a very rough estimate, which actually is enough to explain my purposes for this talk. So it's enough to explain the heavy tails and explain this lattice problem that arises in the specific model. So the time spent in a trap can be very well approximated by beta power h. So the idea here, so this is not exactly true, but somewhat. So the idea is the following. Well, let's imagine you fell down at the bottom of the trap and you want to know how long time you need to exit from it. So if you want to reach this point here, you need to reach this point, beta more times because of the bias. And this time has to be reached beta more times than this one. So basically, if you want to get once here, you need to get beta times here. You need to get beta squared here, beta cube, beta 4, beta h. So the number of visits you have to do at the bottom is beta h so that you have a chance of just getting to the bottom and escaping. So, OK, let's assume this. And I recall the thing that's written on the other part, that the tail of h is, let's simplify, f prime of q to the n. So let's look at what this tells us about the tail of the time spent in a trap. I just take the log. So here something wrong is going to happen at one point. And now I'm going to use this formula here. And this is going to be equal to n to power minus So I'll just rewrite it here in a clearer form. So what you get is probability that the time spent in a trap is larger than n should behave as n to the power minus alpha, where alpha is this number, minus log f prime of q divided by log beta, which can also be written as log beta c divided by log beta, where this beta c I introduced before was 1 over f prime of q. OK, so let's put the computation apart. What happened? I got a polynomial tail. I got an exponent alpha, and the exponent alpha is log beta divided by log beta, log beta c divided by log beta. And in the zero speed regime is exactly when beta is bigger than beta c, so it's exactly when this is lower than 1. So I got my heavy tail. So at this point, you'd believe that the model behaves like a Boucher trap model. It has heavy tails, so you should get all the limiting behaviors that we talked about, stable subordinator, aging, blah, blah, blah. So there is something wrong with what I did in the end. And the mistake is, some mistake that I did myself, is from here to here. So I'll let you 2-3 seconds to imagine how this to this can be false, considering that this is true. When I knew that the mistake was there, it took me quite a while to realize why this is false. So the problem here is that the height or the depth of the trap, h, is an integer. So actually, the probability that h is bigger than log n divided by log beta is actually equal to this integer part. Sorry. And, well, surprisingly enough, this formula here, I'll rewrite it here, probability h bigger than n. So this is only valid for integers. So you can't apply it for this part, but you can apply it for the integer part. And surprisingly enough, this thing here is not the same as this n to the minus alpha. It's different, the long-term behavior. And so actually, it is n to the minus alpha times some function of n. And this function of n doesn't have slowly varying tails. It's some sort of sine type of thing. So it means that all the theorems which are based on sums of IID random variables with heavy tails, they just won't work because this doesn't enter, this type of tail doesn't enter in that picture. So this is the issue that I was talking about. This is what we call a lattice problem, because the values of h are stuck on an integer, and that somehow creates a technical difficulty. So, okay, it's a technical difficulty, and the question is, why is this natural that if there's a technical difficulty, it should have an intuitive explanation. It's just not something that comes out of nowhere. So why intuitively is it that we get this problem for the lattice effect? Why is it that we can't have convergence in law? So in a simple manner. So let me now take the simplified model. It's a Bouchot trap model, but what I take now is directed Bouchot trap model, and the waiting times will be beta power the height. So which should behave exactly as our model. And here the height is integer and has this tail. So if I understand this model, I should be able to understand the biased random walk on the Galton-1 sentry. So the thing that happens is there's going to be a time somewhere in this line where I typically see the first trap of height, let's say, h. And then during a while, my biggest traps are going to be of size h, and then there's going to be a moment after which I start seeing traps of height h plus 1. And if this here is at distance n, this next part here will be at distance n f prime of q, divided by f prime of q. This is something that kind of comes out of this formula that if you want to increase the height by 1, you have to weight a proportion 1 over f prime of q longer. And what I want to do now is, if I'm here or I'm here, I want to argue that the time it takes me to get to here is much shorter than the time it takes me to get over this point. And essentially the idea is here I only have to spend my times in traps of size h, and here I start feeling the traps of bigger size. So if this is point 1, and this is point 2, at 1, where do I see only traps of size h. So I start seeing them here, and here I only see 1, then I see 2, 3, 4. I start seeing more. At the end here, I've seen about, there are 1 over f prime of q of them. And when I'm at the point number 2, I have 1 trap of size h plus 1. So basically, here at 1, the time it takes me to get there is about beta to the h divided by f prime of q. And at time 2, time to get to 1. And then I get beta to the h times beta, time to get to 2. And now if you imagine that beta is a zillion, you see that this quantity here is going to be much, much larger than this one. So what happens is that to get from here to here, I have to start seeing bigger traps which are which have 1 height more, which means I spend a time 1 billion more in those traps, and it's just going to kill, completely overkill the amount of time that I could spend in lower traps. So just by moving a little bit in the environment, I'm going to have to see much bigger traps in which I'm going to spend much bigger time in. So in between this point and this point, there's kind of jump in the law that the time to get to a further point is much, much bigger than it was before. And there's a sort of periodicity going like this. That's here, I typically have one big trap, here I have a lot. And at one point, I start having a lot more time I have to spend to go further. So the idea is, if beta is very, very high, the increase in time you need to cross a trap of just a little bit higher size will overkill all other effects in the system. So basically, the difference of time spent in traps of size h compared to h plus 1 is too big to allow a convergence in law. So now I'm going to state the theorem that we can prove on this model, which is a theorem that was proved by Gérard Ben Arous, myself, Nina Guntert, and Alan Hammond. So it has several parts. First part is that delta n divided by n to the 1 over alpha does not converge in law. We prove this for beta large. So we don't have convergence in law. Yet what we can prove is that the scaling is the right one. It's the right order of variations. And the third and most important part is you can still prove some results of convergence in law, even in this case where we have this lattice effect. So what you see here is that there's a problem between when you cross the typical region when you go from a trap of size h to a trap of size h to h plus 1. But if you get rid of this periodicity and look at the law of the time when you're in this region, and the next region where you start seeing traps of bigger size, there's no reason to have this periodicity effect entering the picture. And so our third result is the following, that if you look along exponentially growing subsequences, so I'll write it like this, beta critical to the n, and you scale by lambda beta critical to the n power 1 minus alpha, this converges in distribution to some infinitely divisible distribution. So instead of having a convergence for every n, we have a convergence along exponentially growing subsequences, which kind of manages to get rid of this lattice effect. So this is essentially what we managed to prove. So in this model, we don't get the long-term behavior of the Bouchot trap model. So does that completely break the universality of Bouchot? So there's this little caveat when you have this lattice effect. But apart from that, Bouchot works really well. And there's an article that was done by Gérard Ben Arous and Anne Hammond. Well, so it's actually two articles, one of which is the both of them, and one of which is Alan, but it's a common work of them, where they actually prove the following thing. If you randomize the bias, I'll be pretty vague on this, and such that the log of the support, no, actually it's, yeah, the log of the support of the bias spans all numbers, well, positive numbers, is not stuck on a lattice. Then the Bouchot picture is correct. So the way you should think of it is if the height wasn't necessarily integers, but could be numbers, so that if you start adding them up, you don't get stuck on a lattice, then you actually have convergence in law. And the limiting law is a stable subordinator, and I don't know if it was proved, but you could probably get aging out of it. So basically, the picture of Bouchot is correct, essentially, except for this little lattice effect. So just to finish kind of talking about this, what I would want to say is that just to explain where this work kind of comes from. So basically, this work here was inspired by work done on one-dimensional random walks in random environments that were done by Enriquez, Szabo, and Zindi, where they actually managed to find a link between directionally transient random walks in random environments and the Bouchot trap model. They managed to make that pretty explicit. And I think that that work was actually initiated by on ideas of Gérard, who was pushing the idea that actually the one-dimensional model should also have this aging, this Bouchot trap model machinery behind it, and he exposed that idea to Enriquez, Szabo, and Zindi, and they managed to actually concretely make this explicit. So they managed to reprove a result of Kasten, Kozlov, and Spitzer, and actually managed to extend that by proving that in one dimension you get aging. So essentially, a lot of this links between like the Bouchot trap model and random walks in random environments were actually initiated by ideas that Gérard got from spin glasses. And so these types of results.
In fact, they were initiated by. Of course, they come from spin glasses, but it came from a remark by Alan Snitman.
Okay. So
in one of his papers on random walks in random environment, he says it looks.
The 06 one.
What?
The 06 one.
He mentions that it looks like aging. So.
Okay. Okay. I thought that was for a different model, but so all this predates me, so somehow it's. Well, I'll just make a very quick drawing of some other results that are obtained. If you look at the percolation cluster, which is basically just you take ZD, and what you start doing is, well, you erase in an independent manner some of the edges. And let's continue a bit here. And you're left with a sort of graph that's complicated. And then you can do a very similar model where you ask, well, if I start doing a biased random walk on this, meaning that an edge going to the right has an advantage, how does this behave? And actually, this behaves very similarly to the types of thing I've been talking about, because the walk can enter areas like this one. Oh, sorry. Whereas if you have a bias to the right, you get here and you start getting stuck going back and forth. So in this model, there are also the straps appearing, and they provoke a slowdown of the walk. And actually, right now, I'm in the process of working with Alan Hammond, who actually, he's been cited a lot of times, is also a postdoc of, an ex-postdoc of Gérard. We're actually trying to prove that in the biased random walk on the percolation cluster, we also have this Bouchot trap model picture. And actually, the conjecture is that if the bias has a rational direction, for example, if it's along a coordinate, then we'll have a lattice effect. Whereas if the drift is slightly off, we'll get stable laws, which is kind of a funny phenomenon that just by changing a little bit the bias, we'll catch the lattice effect, or we might not catch it. Or we might have like convergence in law, or might not have, depending on the small change in the drift. So this kind of sums up where this whole business of looking at limiting laws for random walks in random environments and their link to the Bouchot trap model. In the next class, I want to talk about trapping phenomenon under a different perspective, which is the perspective of the limiting speed. So if you remember, the speed of the biased random walk on the Galton-Wasson tree is supposed to look, with leaves, is supposed to look like this. What I did so far is to explain what happens here, how fast the walk goes. It goes at 0 speed, but to actually manage to show that the right scaling is something of this order. And what I want to do next time is to talk a little bit about mainly open problems about the shape of this part of the curve. Why is it that it would first go up and then it would go down? Is it possible to have things like this? So basically, on these types of questions, we know very, very little. There have been some progress recently, and basically, I want to talk on that. It's work that is strongly related to things that Gérard has been doing. And so I'll expose a few things that we know and talk about a lot of things that are still to be done and probably very hard problems. So that's